A bunch of you responded positively to my stupid gauge pin tricks video, and one of you asked a question that I've been thinking about ever since. Okay, let's do it. Welcome back to Cloud 42, I'm James. Last week I uploaded a video showing how to measure a V-belt pulley groove with a couple of gauge pins and a micrometer, and how to use a CAD program to extract those measurements without having to do any math. If you're interested in that video, there's a card up here, you can go check that out. On that video, I got a comment asking, well, what happens if you don't know the angle of the pulley groove? Because in this case, I knew what kind of pulley I was dealing with, and I looked up the angle in Machinery's handbook. The comment asked, can you use a couple of different size gauge pins to measure at different depths and establish the angle that way? Well, I think the answer is yes, but the CAD program can tell us for sure, so let's take some measurements and give it a try. Now, this is the pulley that we measured last time. This is just one of the drive pulleys on the spindle of my lathe. And the way we did the measurement, we can ultimately, measure the outside diameter and the thickness and the depth just using calipers and normal procedures. But to actually measure the width, since there's no parallel surfaces, we just use gauge pins. We just dropped one in the top, put one in the bottom, and then measured across them with a micrometer, and then use that information in the CAD program to build the model and constrain it. Now, the difference here is that we knew or assumed the angle of the V-groove because my pulley says 3L on it, so I went and looked that up, looked it up in Machinery's handbook, and we picked a value for the angle here. I think it was 38 degrees. But do we really know that? And what if I didn't know what kind of pulley this was? How can we measure it? The plan is I want to actually try this, instead of using one set of pins, to actually use two different sets of pins that are two different sizes. One that sits near the top and one that sits deeper in the pulley. Take two different measurements and then go into the CAD program and see if that will constrain the model sufficiently to determine the angle of the pulley. And, spoiler, it will. But I'm actually curious to see how close we can get with the measurement to what I believe is the actual measurement of this pulley. Let me go grab another set of pins and we'll try this out. Now, I think the pin sizes that I want to use for this, we'll use the smallest ones in this set, 251 and 252, and that's just so that I don't have to walk across the shop to a different drawer where the other ones are. And on the large side, we'll use 351 and 352 because I think these are about the biggest ones that'll fit in the pulley, and they're nice even numbers and that'll be easy to remember. Sorry if you heard a little noise in the background there. The UPS guy just dropped off my Biac scraper that I bought from Keith Rucker. More on that in a future video. Now, I have already taken the easy dimensions off of this pulley for the last video, but I will just go ahead and repeat those measurements here. I'm seeing for the width, 627 thousandths, which I know is about 16 millimeters. For the diameter, I'm seeing 5.436 inches, and then for the depth of the V-groove, I'm seeing 358 thou. I don't know if that's the exact number I got. I don't even know if this is consistent all the way around. We'll just use that. It doesn't really matter because V-belt pulleys do not ride on the bottom. You just have to have clearance. They should contact only on the sides. Now, I selected these sizes of pins to be the smallest and largest that I thought I could use in here. The 251, 252 thou pins go almost to the bottom. They do not touch the bottom of the pulley. They contact on the flank. And in fact, they're contacting on the wear surface that the belt contacts, but as deep as I can get in there without running into surfaces that I don't want to measure. And the 351, 352 pulleys contact up near the top. They do contact the flank, not up on the points. If they were up on the points, we wouldn't be measuring the flank anymore. So I think these are the sizes we need. Let's take some measurements. This is always pretty fiddly, but let's see what we can do here. Trying to make sure that I'm actually on the pin and not hitting something else down there. feels about right. And it looks like we've got 359.5 thousandths. So that would be 5 inches, 359.5. Now let's do that again with the larger pins. Oh, and I hope my micrometer is big enough. Oh, good it is. That is 700, nope, I'm sorry, 801.5. So that's 5 inches, 801.5. Well, those are our measurements. Let's go into the CAD program, throw this all into some constructive geometry, and see how close we get to the 38 degrees that I think this is. In the last video, I kind of rushed through some of the CAD drawings, so I'll take a little bit more time today and explain a little bit better what I'm doing. Let's start with a sketch. Put it on this plane, and I'll click Look At to bring this up parallel to the camera. Now, I get lots of questions about how I move so smoothly around the 3D models like this, and the answer is I'm using SpaceMouse, which is a three-dimensional controller that I can, pull up and down, side to side, and rotate on with 6 degrees of freedom. And it makes it really easy to move around in the model. Best $100 I've ever spent. It actually was a tip from a viewer who suggested it after seeing how I was zooming in and zooming out and navigating around in the models. There's a link in the video description. I'm not really trying to hawk these things, though I get questions in every video, so I'll just head that off here. So let's start by talking a little bit about constraints. If I just hit L for line and I just draw a line, you'll note that it is light blue. And the reason it's light blue is because it is unconstrained. I can move it around, I can change the angle of it, and it moves freely because there are no constraints. If I put some constraints on it, so I'll select those 2 points and I'll click Coincident, and then I will move this up here and I will click on this and I will click horizontal vertical and it will snap it vertical. You'll note that it has now turned black when it's not selected, and that means that that line is constrained. Now the point here at the top is still open, and that's because we haven't set the length. But if I hit D for dimension, set that length, then now that's closed and this line is fully constrained. No part of it can move. And we will use this fact in a little bit to tell when we've fully constrained our sketch of the pulley. So let me delete that and let's just create a new sketch. And let me start by sketching out the pulley. Now I'm going to hit L for line and X for construction. You can see over here the line type is set to construction, and I will just start drawing in my construction lines. Now if I click on a point, it will automatically create a coincident constraint there, and if I bring this over to the point where it snaps vertically, then when I place it, you'll note it has already placed a vertical constraint here, and at this point a coincident constraint. So that line is now black. The length doesn't matter, I'm just going to use it as a mirror line, but now it is constrained. And I will do exactly the same thing to put in a horizontal line, and those are my mirror lines and they're constrained. Now I'll turn off construction, you can also hit X, hit L, and let's just sketch in the pulley. Now I'll draw a piece of baseline here, and then we'll draw up, over, down at an angle, and in. Now this is just the rough shape of 1/4 of the pulley, and we will start mirroring this. So I'll select those by holding Control and selecting all of those lines. Click Mirror, mirror line around this center line that I just drew, and now we'll do exactly the same thing. You hold Control to select all of these segments, and I will then mirror those around this x-axis line. And now we have the general shape of the pulley, but you'll note it's all still blue. We've got a whole bunch of these little constraints, and those are mirror constraints. So if I try to move these, it constrains, the position of this line constrains where this line and this line and this line are located. Same thing with the lengths of these. but they're not fully constrained, so they're still blue. So let's start adding some dimensions. I'll hit D for dimension, and we know that the overall outside dimension of the pulley, because we measured it, is 5.436. Now when I hit enter here, watch what happens. The entire sketch scaled. If you just open up Fusion 360 and you try to do this, you'll note that it will shrink that line that you put the dimension on, which will then distort the rest of the sketch. But if you come up here to Preferences, and in Preferences on the Design tab, there's a checkbox here that says Scale Entire Sketch at First Dimension, and I have that checked. So when I put that first dimension on there, it automatically scaled the entire sketch. And that again is a tip from a viewer that somebody saw me flailing and put down in the comments. So let me hit dimension. Let's put some more things on here. I'll put on the width of the pulley. Now when it tries to change this dimension, it won't scale everything because we already have a dimension on there. So 0.627. And you can see it ended up turning part of this inside out, and I will just go ahead and move these lines around to try to get it to something reasonable that matches my intent. Okay, and now we have another dimension, which is the depth of the groove, 0.358. Now it's hard, because none of this is constrained. When I move these horizontally, it just moves the entire line. It doesn't change the angle. We'll get the angles constrained here when we start drawing in the pins. And let's do that. So create circle, and let's put in a 2-tangent circle. Let's do a small one and a bigger one because we've got that on both ends. And I can't mirror these because the pins are different sizes. But I can come back in here and put on the dimensions. So D for dimension, and we'll make this one 251. And this one 351. Great, and down at the bottom, this one will be 252, and this one will be 352. Now you'll note that even though we have dimensions on them, they're still blue. And the reason they're still blue is because they can still move vertically. So we need to constrain them vertically, and we'll do that by putting on the outside dimensions that we measured. So D for dimension again, right click to say pick circle arc tangent, and I will click on the small circle and come down here, click on this one, and the dimension across those pins that we measured was 5.3595. Now that's positioned those, but because these angles are not fixed yet, this stuff is all still blue. So let me do exactly the same thing, pick circle arc tangent, and let me put in the measurement across the large pin. And we know that's 5.8015. And it has now snapped in. It's solved this, and everything is now black, meaning that nothing can be moved. It's all fully constrained. And ultimately, I'm trying to move these, and they're not moving. They can't go side to side because they're constrained between angled lines that are mirrored around this center line. So the center of the circles is necessarily constrained to that line, even though there's not a unique constraint for that. But in general, when you are modeling, this is what you should be trying to do, is get all of the lines black. You want to put in this case, we've put in only things that we have directly measured and that we know as facts, and everything is constrained in black. That means that we have fully solved this, or the software has fully solved this, and we can say that we think this angle is correct because it's fully constrained. The software thinks we fully defined it. Now let's see what it actually came up with. Now remember, when we looked this up in Machinery's Handbook last time, a 3L pulley over 4.2 inches, we expect it to be 38 degrees. Now this angle can go anywhere between 32 and 38 depending on the diameter of the pulley. We expect it to be 38. Let's see what it actually is. So I will hit D for dimension, click here, and it looks like it's going to try to place this at 34. I'll click. Adding this dimension will over constrain the sketch. That's because everything is fully constrained, so I don't need to define this angle, and if I did, there would be no way to solve it. So I'll click OK to create a driven dimension, and it will put that in at 34 degrees. So we have measured this at 34 degrees. Now, why is that not 38? Well, I don't know. Maybe the pulley really is 34 degrees. To get a little bit more confidence in this, let me try a couple of things. Let's try to figure out how sensitive this is to these dimensions. Now, I took these measurements multiple times. You only saw one on camera, but I took them multiple times, and across the set of large pins, 3 measurements all came out within 1/1000th of an inch of each other. It's kind of fiddly to feel them. And across the small pins, it was within 1/2 thou. So let's see how much of a difference that makes. So this is 5.8015. Let's make that 8025 and see how the angle changes. And that changed by 1/10 of a degree to 33.9. What if we had an error as big as 0.005 of an inch, which is, a lot for this kind of measurement. So instead of 5.8015, let's change it to 5.8065. And that's changed to 33.5 degrees from 34. So not a huge difference, and that's a pretty large measurement error for a micrometer, and it doesn't change this very much. So I have a lot of confidence that this angle really is 34 degrees. We could go try to measure it in some other way. I'm not going to bother now. You can feel free to try that on your own. But I'm pretty confident this is 34 degrees. And again, that's because we only put things into this sketch that we know for sure because we measured them, and Fusion 360 has turned everything black, indicating that it was able to fully solve and fully constrain everything. If there was something in here that was still blue, then we would know we hadn't measured enough to actually get an answer to our question. Now you can do exactly the same thing with dovetails. Just draw up 1/2 of the dovetail, mirror it around a center line, put in the dimensions and then putting your tangent pins on the inside of the dovetail, and then measure, depending on how you had to measure, either between the pins, if it's an inside dovetail, around the outside of the pins, if you're measuring on the outside of the dovetail, and you can use different size pins, and you can do exactly the same technique. Any place where you have known reference surfaces, you can constrain the pins in an angled groove. You should be able to do something like this. So I'm satisfied that we got an angle. It's not what I expected. Is this a poorly machined pulley? Is it made to the wrong specs? Is it not really a 3L? I don't know. But it's really not that sensitive, and this is going to work fine. What's going to happen here if this is too narrow is it's going to constrain the belt near the top. The belt's going to wear in. You might have a little bit more friction and a little bit more wear, but this is an import lathe. What really did you expect? So it's certainly close enough for a V-belt to run properly at this scale and at this kind of power level. And this is a useful technique that you can use for making these kinds of measurements. Okay. I went back out in the shop and got out my angle gauge set and actually tried to measure the angle of the pulley groove. Now, it's hard to do because I can't actually stack up the different angle blocks and get them into the groove. It ends up being too thick. But I was able to get the end of a 30-degree angle block into the groove of the pulley. And as you can see, there's just a little bit of a gap there, and 34 degrees seems very, very reasonable. So as a sanity check, yeah, I think our measurements are pretty much right on. And because they are so precise and because it's constrained, I have a lot of confidence in it. So why is this pulley machined to 34 degrees? Well, it's a step pulley, and so there are several different diameters on it, and I checked them all, and they are all at pretty much the same angle. So it seems clear that they just simplified their machining process. Instead of actually putting the correct different V-groove angle on each pulley diameter, they either used a form tool or just used the same CNC program and used the same angle and just cut all of the steps in the pulley to the same angle. And 34 is actually a pretty good compromise for these sizes. Well, that's it for today. If you enjoyed this video, please give it a thumbs up. Feel free to subscribe to the channel and leave me a comment. I'd like to know what you think. I always learn something from reading the comments on my videos, so leave your best stuff down below. Thank you for watching.